So in this case, the data set has been changed slightly just to show you the effectiveness of blocking and whenever there's something that is heterogeneous, which means that it is not homogeneous. Heterogeneous means it is not all equal or smooth. So in your question 5, what happens if there is greater heterogeneity across blocks? In this case, for block 1, I had doubled all the numbers, and you will see that block number 1 is outstanding. This is a case when blocking is actually useful because it will weed out the variability where you usually would have an influence. Because if you were to calculate the mean within your treatment number 1, the mean between your treatment number 1, these extreme values are going to pull your mean up for no reason. But in blocking, it will allow you to protect yourself from this extreme blue line. If we take a look at the outputs, what can you say about the new outputs of response 2? The same way you have one with ANOVA and one without ANOVA. So in this case, you can take a look at the model. Your F values are fine. One model without blocking is actually less significant. This is a case where blocking is becoming useful because it is protecting the integrity of your F value. You'll see that the one with blocking actually generates a higher F value. We know from the previous example that R squared is a little bit inflated, but this inflation, if you keep in mind, then you know what comes out from it. Is it really 0.8477? It's not. It's a little bit more inflated. But in this case, with an R square of 0.1542, it doesn't explain your entire model because in this case your F value is insignificant and therefore your model would not be good without blocking. If you take a look at the results of your blocking, treatment, and block and treatment interaction, you will see that blocking was effective because it is significant. It worked out, it was able to weed out that extreme value. In terms of treatments, you can also see that now there is an actual difference from one treatment to another. Whereas in the top output, the treatments are insignificant. In terms of the interaction, once again, unlike two-way ANOVA, you're not looking for an interaction. You're looking for homogeneity within the blocks. So therefore, you do not wish for an interaction to happen. If there was an interaction, it will show that the blocks are different from each other and there will be bias from the blocking to the treatment. So in this case, blocking worked, your treatment is okay, and your interaction does not appear, which is a great thing. If we take a look at the summary, then you will see that there is something a little bit odd with block number 1, which is a little bit more extreme. In this case, blocking will weed out this blocking number 1. Perhaps the researcher was interviewing in a slightly different method, and it generated higher values than others. You'll also see that the grouping of 1 is under A, and if you take a look at the comparison pair by pair, everything that is highlighted has to do with the comparison of 1 and the subsequent all other blocks. So in this case, you have 1, 2, 1, 3, 1, 4, 1, 5, 3, 1, 3, 4, 1, 5, 1. Okay, so in this case, it's very, very obvious that 1 was an extreme value, and otherwise, without blocking, you would not have been able to generate a valid model. If we take a look at the treatments on the other end, we would look at whether the treatments have different means or not. So the same way to interpret it, you'll see the grouping. that if you were to use the method of 4, 5, and 1, it will generate the same performances. And the same thing for grouping number B and C. If we look a little bit closer in the comparison, then you can weed out the differences. And this is an interpretation just like one-way and two-way ANOVA, just to see which treatment is better and whether there were some treatments that are better than others that generated more performances. In this case, 451 is a little bit higher than the rest, which is 2 and 3. Now we'll look at response number 3. What happened if there's only one observation in the block design? I took out all of the observations on one side and allows you to look at each treatment with only one observation. Whenever you're running an ANOVA, which is an analysis of variance, you need more than one number in order to create variation and standard deviations. So in this case, if I were to just plot it, the mean of one number is the number itself. There's nothing striking, nothing that is extreme, so I can keep it this way. However, if we look at the outputs, you will see I could not generate the regular output. And you will find in the in-class exercise that I will show you an example that is very similar. And in order to run something like this with blocking, you would actually take away the interaction term. That's the only way you can salvage the fact that you only have one observation per treatment. In other words, in response 3, the better choice in this case would be to run it as if it's a one-way ANOVA and look at the treatments. But if you want to run it with blocking as well, then you can take off the interaction term and evaluate your output as it is, knowing that for blocking, you do not want any differences. And for treatments, you do want differences because that will allow you to see whether one treatment is better than another. So keep in mind, every single topic has a table on its own. This specifically, the logic behind your F value and how to calculate it is the same. And more specifically, you're going to look at block in the treatment. That's what will allow you to evaluate whether blocking worked or not and whether your treatments have differences between their means. Here is the equation. We do know that SST is equal to SSE plus SSR. In this case, we're going to replace what is being explained by SSTR, which is the sum of square of treatment and the sum of square of blocking. You do not necessarily need to calculate this by hand, but do know how these values come from. So here you have the Yij, which is specifically the value of that specific treatment, minus the means of the means, which you can see in your marginal means table. So just know that SST is equal to everything that is being explained plus everything that is being not explained. If we take a look at the full equation, you have your common components, which acts just like an intercept. Then you have the treatment effects, and you also have the blocking effects. This is in fact a B and not a beta. This would become your randomized block equation. And note that all of the assumptions where the error terms are independent, that it has a normal distribution, and that these variances are constant still apply. Therefore, in order to test, if I were to ask you to test for the treatment effects, you can write down your hypotheses, figure out your F critical, and figure out your F observed based on information that you have, and make your decision to conclude whether there are differences from one treatment to another. You can also test for blocking effects. And of course, these came out from the outputs, but you can calculate them manually. Therefore, F observed, find F critical, and make your decision. If you were to reject HO, then you conclude that the blocking effects differ. It means that if you do reject HO, it means the block effect has helped you enhance the power of the F-test and the experimental design. If you do not reject HO, it means that your blocking was not effective. So similarly to our previous topics, you can also calculate the confidence interval. In this case, you would take into account the number of blocks.